Okay, in this lecture, we are going to leave the basic of the linear algebra and property theory. Let me start with the linear algebra. What is the linear algebra? Linear algebra provides a way of the compactly presenting or operating on set of the linear equation. So what is the linear equation and what is the set of linear equation? We will learn this on today's class. So Bayesian linear algebra is one of the most important branches of the mathematics to know when it comes to the machine learning. In this lecture, I'm not going to show the comprehensive survey of all about machine learning and linear algebra. We are just going to be focused on the subset which are more and most relevant to the machine learning. Actually, I uploaded some material related to the linear algebra and property theory in the Blackboard website, so I highly recommend you to self-study what is the linear algebra and what is property in machine learning or deep learning field. Okay, let's start. Let me start with the basic element in linear algebra. The first one is scalar. What is scalar? Scalar is the single number. It can be the integer or real number or rational number, something like that. So integer is like the 1, 2, minus 3, something like that. So the real numbers means like the 0.1 or minus 0.23, something like that. Generally, the scalar value is denoted with the italic, like the a and x, something like that. Then what is a vector? Vector is the 1D array of the numbers. Let's say a vector x is equal to x1, x2 through the xn. So, for example, the vector x will be the some kind of 1, 2, 7, something like that. Vector y equals minus 3, 6, 6, something like that. So this is examples of the vector. The example notation of vector for types and size is like this. So as you can see here, R means a real number. So it means that this vector is consisting of the n entry with a real number. Okay, so more generally, we would refer to a vector x as a x lies in the R superscript n, something like this. So this is a vector. Then what is the matrix? So matrix is a 2D array of the number. For example, the matrix A is equal to the A11, A12, A21, A22, something like that. So for example, the matrix A will be like the 1, 3, 4, 6, something like that. Or matrix B will be the more higher dimensional, more higher dimensional values like the 1, 3, 3, 2, 6, 7, 0, 0, 0, 0, 1. Okay, something like this. So example notation for the matrix, it looks like this. So it means that this matrix consists of the real number with the m by n size. What is m by n means? So generally we call the size of this part as a n, size of this part as n. So we generally call this part is rows and this part is column. Okay, so the size of matrix means that it consists of the m rows by n columns. Okay, so let's see. What is the size of this matrix A? A lies in the integer 2 by 2 because it consists of the 2 rows and 2 columns, and B lies in 3 by 3 because it consists of the 3 rows and 3 columns, something like that. So this is the Bayesian notation of the matrix. So more generally, we would refer to the matrix A as A lies in the R superscript n by n. Okay? Then, what is a tensor? Speaking loosely, a tensor is a more general terminology that contains every Bayesian notation so far. For example, if it has the 0 dimension, it is called the scalar. If it has a 1 dimension, it is called the vector. Okay? And if it has the 2 dimensions, it can be called the matrix. And a tensor can have a 3, 4, or more higher dimensions. Okay? Actually, the concept of tensors, general terminology of these kinds of things. So tensor have application in deep learning, especially in image analysis. Okay, let's see the example. So here's the example. This is the vector x. So as you can see here, vector means the element, each element like this. So in this case, vector x consists of the 64 entry, something like that. So it is represented by this, like this. Another example is the matrix. As I mentioned before, the matrix size of matrix can be represented by row by column, something like this, columns. In this case, there are 8 rows like this, and there are 8 columns like this. So the size of matrix will be the R8 by 8, something like that. And the tensor, I mean 3-dimensional space. Tensor in 3-dimensional space looks like this. So comparing to the vector and matrix, it has the one more dimension like this. So comparing to the matrix, it has the, let's say, row, let's say, have columns, and one additional dimension is called the channels like this. So in this case, there are 4 rows and there are 4 columns, and there are how can I draw it? There are 4 channels like this. Okay, so in this case, the size of this tensor is the R superscript 4 by 4 by 4. Okay, this is a case of 3D space. A representative examples of the tensor is the color image. Generally, a single color image is represented as a 3D tensor. Let's see the example here. So this is a color image. As you can see here, color image consisting of the 3 channels. Let's say red, green, blue, something like that. In the image, each channel is a matrix with a size of n by n. It means that, okay, as you can see here, this is an example of image. Each image has the width, or called the row, and height, with also or called the column, and 3 channels, something like this. And each pixel, like this pixel, has 3 values, like the 4, 9, 35, something like this. So in this case, the size of this image, let's say A, will be the R 4 by 4 by 4 by 4 by 3. Okay? So this is the tensor representation of image. Of course, you can represent this image like this, 3, 4, 4. Because if you first think about this channel and then consider this height and width, you can also represent like this. Actually, it depends on which dimension you choose first. But in the image, we generally start with the row, column, and channel. Okay, so this is the tensor representation of image. So to apply some operation on the image, we have to know the matrix or tensor operation, which is the core of the linear algebra. And today we will learn about this operation or some terminology. Okay? I'm not sure how many of you are familiar with the deep learning or deep convolutional neural network. But in a course, you will learn what is the neural network, convolutional neural network, deep learning, so don't be afraid. But in this lecture, we just see what is the convolutional neural network and what component makes the convolutional neural module. Okay? So the convolutional neural network is the fundamental element of the deep learning. The most popular one is VGG network and residual network. So VGG network was published in 2015 maybe in ICLR conference, and residual network was published in CBPR 2016. So actually it was the best paper award. In the 2 years ago, this paper was the most cited paper in the whole area in computer science or electrical engineering field in Google Scholar metric. I guess this paper will be the most cited paper in the world near future, because the most deep learning or the deep learning related technique use the residual network as a simple element here. Anyway, we will of course learn this residual network in this course. You can see here, this is the network architecture of the VG network. As we discussed previous slide, the image can be represented by the 3-dimensional tensor like this. So in this case, this will be the 224 and 224 with the 3 channels. Let's say RGB here. So from this image, each convolutional module generate another 3D tensors like this, and this. Okay. So as you can see here, each element of the tensor is also a tensor represented the 3 dimension or 4 dimension, something like that. This 3D tensor is also called the activation or feature that represent an image more robustly and discriminatively. Anyway, so this tensor representation is a core in the deep learning. Another example here, this is a residual network. It consists of so many layers, more than the 115 layers, but in each layer, it also consists of some kinds of the tensor representation like this. Actually, it is called the convolutional parameter, but don't be afraid, we can learn these all of things in this course. But anyway, this time, please remember the tensor representation is the core in deep learning or machine learning field. Okay? Okay, let's move on to another terminology. It is the matrix transpose. The transpose of the matrix results from the flipping row and columns across this diagonal arrow. Here is the example. The transpose of the original matrix A with A11, A12, A21, A22, A31, A32. The transpose of the original matrix is going to be a new matrix with the size of 2 by 3 with the element A11, A21, A31, A12, A22, A32. Okay, so in this case, the size of the original matrix was the 3 by 2, and the size of a transpose matrix A is 2 by 3. Okay, so as you can see here, this element is moved to this part. This element is also moved to this part. So transposing a matrix essentially involves the switching index of the rows and columns like this. So the matrix transpose operation has a nice desirable property as follows. So the following properties of the transpose are easily verified. So I would say you can do this by hand and yourself, because it will be the really important property that can be applied to the many kind of machine learning application. Okay, let's see the detail. For any two matrix A with size m by n and matrix B with size of n by p, the transpose of A matrix is equal to A. Okay. Another one is transpose of A plus B in bracket should be A transpose plus B transpose. Third one is the transpose of scalar times matrix A will be the scalar times transpose A. Finally, the transpose of A times B should be P transpose times A transpose. So this is the basic property of the matrix transpose. Okay, what is the next? Next is the matrix multiplication, or called the product. So for any two matrix, let's say A with size of n by n, B with size of n by p, the output of this matrix multiplication can be represented like this. So each entry, let's say the C subscript I comma j of output matrix C is the summation of each entry of the A ik times B k p k j. Okay, what does that mean? Let's see the example. Okay, let's say this is a matrix A, this is a matrix B, like this. Okay, so it will be the matrix C. Okay, so to compute this part, okay, this is the C subscript 2 by 3. Okay, to compute this value, we multiply this row vector and this column vector. This is the A21 and this is A22, and this is the P13 and this is P23. Okay, so to compute this value to C23, we can multiply the A21 with the P13 plus A22 times P23. Okay, so it can be represented like this. So the summation over A2 comma K times P K3 from K equals 1 to the 2, like this. So as you can see here, each element of the output matrix can be generated by this simplification. Okay, I suggest you to do this matrix multiplication by hand. This will be the basic element in the machine learning. Fortunately, the most matrix multiplication operation were coded and programmed by the many libraries. So actually, you don't need to implement or apply this multiplication by yourself, but it is really important to understand what is the matrix multiplication. Okay? So in matrix multiplication, it is useful to know the few basic properties at a higher level. Suppose any two matrices A with the size of n by n and matrix B with the size of n by p. First of all, matrix multiplication is distributive. What does that mean? The x times a plus b in brackets is equal to x times plus x times b. This is the distributive law. Another one is the matrix is associative. Associative means x times a times b bracket is equal to x times a in bracket times b. So it means that we can compute the matrix multiplication without considering the order. So these two basic rules can be generalized any kind of the matrix form. Let's say it can be generalized like the with more variable like this, and associative rule also can be represented by like this, like this. Okay, so this is a two general property of the matrix multiplication. Another thing is the commutative. In general, the matrix is not commutative. It means that A times matrix B is not equal to the B times A. Okay? So if you're not familiar with this property, take a time to verify them in yourself with some material. Okay, let's move on to the identity matrix. What is identity matrix? Identity matrix is a matrix that has the 1 along the diagonal and zeros elsewhere. Let me see the example. So let's say identity matrix with 2 by 2 will be the 1 0 0 1 like this, and identity matrix with 3 by 3 will be the 1 1 1 along the diagonal and zeros elsewhere like this. So this is the identity matrix. It has a nice property that can make the programming more efficient. Let's see the example. Okay, for example, for all the matrix X lies in the integer space with a size of n by n. No, it's not an integer space. It's a real space, n by n. X times the identity matrix is equal to identity matrix times X is equal to X. Why it is important? So with this this distributive law, we can verify this equation easily. As you can see here, x plus y times x plus z times x is equal to x times I plus y plus z in bracket. So matrix multiplication is significantly more intensive than the matrix addition. So what does that mean? So in the left hand side, there is the 2 matrix multiplication and 2 summation here and here. In right hand side, there are 1 matrix multiplication and 2 matrix summation, something like that. So it means that these 2 operations can generate the same output, but when compute this part, we need one more matrix multiplication than the right hand side equation. So the left hand side will be slower than the right hand side as matrix dimension is increased. So by using the identity matrix, we can make the equation more efficiently and we can make the sum machine learning technique more tractable using the identity matrix. Okay, now we have a Bayesian notation in linear algebra. Speaking loosely, linear algebra provides a way of the compactly presenting, operating on a set of linear equations, something like that. So then let's start what is a linear equation. Okay? And then let's see what is the system of linear equation. Okay, so linear equation is like this. So the linear equation is the combination of the linear terms of the variable x1, x2, xn with some coefficient a11, a12, a1n, something like this. So this is the examples of the linear equation. So linear equation is just consists of the single variable. So if there is some nonlinear terms like the x1 times x2 or the square of the x1, something like that, this is a nonlinear element. So the equation that contains this nonlinear element, it's not a linear equation. Okay. So this is a linear equation. Then what is the system of linear equation? Actually, this is also called the linear system. Actually, linear system is just one or more equation than the linear equation, single linear equation. So in this case, the systems of linear equation represent this single is linear equation, and the set of the linear equation is a system of equation. Okay. So why we learn the linear algebra? The science or the machine learning technique can be represented by linear equation or the systems of linear equation, but as you can see here, given the coefficient values with the right hand side values, we want to find the x. We want to define the x is unknown parameter values, and we want to find this value x from this coefficient like a1, a12, b1, something like this. But as you can see here, if we deal with this linear equation, this is very complicating, and this is hard. It is hard to deal with. So by using the matrix notation, we can simplify this linear system like this: ax equals b. So we can develop a computationally efficient way to solve this linear equation using the matrix form. Okay, that's why we are learning the linear algebra to solve the machine learning technique. Okay, so this is the systems of linear equation. So systems of linear equation can have three kinds of solution. Let's suppose we have a very simple linear system, two equations with two unknown variable. For example, like the 2x1 plus 3x2 equal 6, 3x1 plus 7x2 equals 1, something like that. So we can draw this linear system on the x1 and x2 domain like this. Okay, so we can draw the values that satisfy the equation as a line. So in other words, the values that satisfy the equation are going to be on the line. Okay, so let's say there is one like this. Okay, whole point on this line satisfy the first equation. There is another line here that satisfy this equation. Actually, this is not mapped exactly, but let's just assume that there is two lines like this. In this case, the single point here, a single point to simultaneously satisfy the first and second equation. So in this case, the linear system has a exact one solution. Okay, so let's take another example. If two lines like this and like this, they'll, okay, I will move to the like this. Let me draw like this. So as you can see here, there will be the infinitely many solution because each point to satisfy the two equations simultaneously. So in this case, we can say that there is the infinitely many solution. Okay. The last case is the no solution case. If there is the line like this and like this, these two lines are not going to meet forever. So in this case, there is no solution that simultaneously satisfies the equation. So if there is one solution like this, the multiplication by matrix is an invertible function. I mean, like this. If the system is represented by AX equals B, and if there is one solution, this matrix function is invertible. Okay. Okay. So what is the matrix inversion? What is the invertible matrix? If the matrix is invertible, there is the inverse of the matrix A. This. So with this inverse matrix, we can make a identity matrix that we discussed previous slide. So what can we do with this matrix inverse? We can solve the linear system using this inverse. Okay, let's say we have a AX equals P system. We can multiply the inverse of matrix on the left hand side like this and right hand side like this, because we already know this will be the identity matrix and this will be just X as we discussed previously. So vector X will be the A inverse X A times B. So in this case, the solution X is equal to A inverse B. Okay, this is the solution of the linear equation. Actually, this procedure is not numerically stable, but it is useful for abstract analysis like that. Actually, there is a numerically stable method to solve this linear equation, but this will be the out of scope of this lecture. So please find the way to how to solve this linear equation yourself. Okay. So in the AX equals B, the matrix can not be invertible if there are more solution than columns, more columns than rows, and the redundant rows on column. It is called the linearly dependent on row-like cases. In this case, the matrix cannot be invertible. It means that we cannot solve the linear system like this. So we need another procedure to solve this problem. So let's say a square matrix with size of n by n with a linear dependent column is said to be the singular case. Okay? I would not deal with all of things today, but we should self-study this concept by material that I uploaded on the website, or you search on Google or YouTube about this. Okay? Okay, let's move on to the norm. So norm is a function that measures how large a vector is. It is similar to the distance between vector and the point represented by the vector. More formally, a norm is any function that satisfies these three properties. So if f over x is equal to 0, so x is equal to 0. What does that mean? So f over x should be always larger than 0. Okay? The second property is the triangular inequality. F over x plus y should be lesser than the f over x plus y, f over y. It will be the triangular inequality. Another one is the homogeneity. It means that f over scalar times vector x should be scalar times f over x. Okay, so this is the last property of the norm. So there are many popular norms that satisfy these three properties. One of the most popular one is the LP norm, called the LP norm. It is notated like this with subscript p. So general form of the LP norm is like this. Okay, so machine learning or deep learning area, it is often used to know the length of the vector, similar to the distance. So especially when it involves the computation of the loss function. So we can study what is loss function in the later, but anyway, we generally use the LP norm like this in machine learning stuff. For example, the most popular norm is the L2 norm. L2 norm means P is equal to 2. Another example is the L1 norm. When P is equal to 1, so it is represented like the summation of the absolute value of the element xi, like this. Another example is the max norm. Max norm means that P is equal to infinity. So max norm can be represented by like this. So what does it mean? These norms can be illustrated like this, and this. It means that the point in the lines have the same norm value. In case of error norm, these values should have the same distance or same norm. In L2 norm case, these values should have the same norm or same values. In max norm case, these rectangular values should have some same values, same norm values. So it means that, let's say in these 2 points, in terms of distance, vector distance, this point looks like larger than this, but if we use the max norm, these two values should have the same distance. Okay, this is the definition of the norm. Okay, the last concept in the linear algebra is the decomposition. Why should we learn the decomposition? Decomposition of the function of the value can tell us a lot about their property. Let's see the example. Integer into the prime factor, like the 12 is equal to 2 times 2 times 3, tell us about any multiple of the 12 will be divisible by 2 by 3, 2 or 3. Okay, so it means that this decomposition, this integer value decomposition can provide the property of these values like this. Okay, the matrix decomposition serves a similar function. Okay, let's see the first example of the eigenvalue decomposition, called the eigendecomposition. So eigendecomposition are breaking up of some matrix into the eigenvectors and eigenvalue, like this. Here is a formal definition of the eigendecomposition. The formal definition is AX equals the lambda x. It means that given matrix, square matrix A, here, given square matrix A, eigenvector is a non-zero vector that multiplying it by x only alter the scales of x, like this. And lambda is the eigenvalue corresponding to the eigenvector. So intuitively, this definition means that multiplying scalar matrix A by the vector x results in a new vector that points in the same direction as x, but scaled by a vector lambda. To summarize, so this will be the eigenvector, and this will be the eigenvalues, like this. So why we learn the eigendecomposition? So every linear symmetric matrix can be decomposed into the eigenvectors, eigenvalue, like this. This is the diagonal matrix consisting of the eigenvalues of eigenvectors contained in the eigenvector matrix X, like this. So by using the eigendecomposition, we can decompose every linear symmetric matrix as like this form. It means that this matrix form is more easier to deal with than the previous matrix in the original, like the original matrix A. Okay, so what does that mean? So let's say we want to solve the linear system AX equals B, which is the core of the linear algebra. Actually, this AX equals B is really hard to find the solution vector X. But if we can decompose matrix A as a X sigma X diagonal matrix with the X transpose, comma vector X, something like this, using the eigendecomposition, we can make the problem more tractable. So that's why we learned the eigenvalue decomposition or eigenvector decomposition. There is another decomposition method. It's called the singular value decomposition. That can be that can be represented by this. This is a more general method of decomposing any linear matrix, because in eigen decomposition case, we only consider the linear symmetric matrix case, but using singular value decomposition, we can deal with any kind of real matrix. So this is more general decomposition method comparing to the eigenvalue decomposition. Okay? Okay, from now on, we'll talk about the basic probability theory. So probability is the study of the uncertainty. It is at the heart of the machine learning algorithm. So most machine learning methods involve the use of the random variable probability distribution, and most unsupervised method use the discrete probability distribution, Bayesian analysis, something like that. So I guess you might know, you might heard about what is this, but you don't know. I guess you don't know what this exactly is. So in this lecture, we can learn the what are they meaning. And in this course, we will learn the some supervised and unsupervised learning and how they use the terminology of the probability. Okay. Okay. Let's start with the random variable. Okay. So what is the random variable? So random variable means the variable which takes the values according to the probability distribution. Okay, let's see the example. Okay, let's define a matrix X is equal to a set of some number x1, x2 through the xn, something like that. We can say that each xi can be source of a random draw from the some distribution with the some parameter. Okay, what does that mean? Okay, let's say if this random variable was derived from the Gaussian case, it can be represented by this with the some parameter mu and sigma values. Okay, so it means that if we know the what is mu and what is sigma, we can define the probability distribution of this random variable. So that's why we learn the probability distribution function. So random variable can be the discrete form that takes infinite and countable infinite numbers of values. Here you can see this is the discrete random variable case. As you can see here, in discrete case, the random variable would be the 0.25 or 1, something like that. So this is the discrete random variable. So random variable also can be continuous value that taking infinite numbers of value like this. Here there is the infinite the continuous number in continuous case. Okay, so random variable can be the discrete or continuous value. So what is the probability distribution? The probability distribution describes the likelihood or probability that a random variable will take on a certain value. So this is called the probability distribution. It is dependent on the discrete or continuous random variable. So in discrete random variable case, the probability distribution will be the probability mass function is called the PMF. In continuous random variable case, the probability density functions called the PDF is used. Okay, so this is the property distributions. So the property mass function PMF is a function P that must satisfy that. So P over X should be larger than 0 and lesser than 1. The summation of the probability across the whole random variable should be 1 because this is the probability. And the PDF is similar. The PDF is a function P that must satisfy that. So the function P over X should be larger than 0. The integral P over X dx should be 1, like this. So this is a property of the PMF and PDFs. When given two random variables X and Y, you may be interested only in the distribution of the one variable. Let's say X or Y. Okay, so that's why we learn the marginal distribution or marginal probability. We can accomplish this by marginalizing the distribution through the summation or integration. Let's see the example. So if we want to find the probability of X, we can compute the summation of the P, X, and Y. I mean, this is called the joint probability. So this joint probable distribution can be decomposed into the conditional probability and probability of Y. But we can see the probability of the X can be represented and can be computed by the joint integral of the joint probability. This is the marginal probability case. So what is the conditional probability? We are interested in the likelihood on an event occurring given another event is occurring. In this case, an event will be the X, another event will be the Y. So the conditional probability X by Y is equal to the Pxy over Py, like that. This is the conditional probability. This is a heart of Bayesian theory or Bayesian theorem. We will run this part in the later course. And there is the chain rule of the conditional probability. So joint distribution can be decomposed into the series of the conditional distribution. What does that mean? So this is the joint distribution with the variable x1 through the xn. Then we can decompose this with the probability x times probability xi by x1 through the xi minus 1. What is that? We can write down like this: x1 p x1 x2 per x1 and p x3 by x1 comma x2. Finally, pxn is equal by x1 x2 through the xn minus 0, something like that. This is the chain rule of the conditional probability, because we already know that this conditional probability can be represented by this. We can compute this part separately. Then we can derive another equation, but in this lecture I cannot deal with this part, so I would suggest you should study this part yourself. Okay. So the another concept is the independence. So what is independence? Independence imply this joint distribution is equal to px1 times px2. It means that these two random variable is independent each other. Okay, so another terminology in probability theory is the expectation, variance, and covariance. So first of all, so expected values of random variable x is the average values of random variable over that function. What does that mean? In this case, so expectation x is equal to summation of xi times pxi. So this is the expectation of random variable x. In continuous case, this expectation can be represented like this: integral x times p over x dx, something like this. So this is the expectation. So what is variance? The variance is a measurement of how much variance exists within the random variable. So the variance over x is equal to expectation of the square x minus expectation x, like this. So this is the variance definition. So final one is what is the covariance? So covariance measure the extent to the which one random variable increase or decrease with another random variable. What does that mean? Actually, the covariance is very important for measuring the property of the models and relationship between the variable. It is defined like this: the covariance x comma y is equal to expectation x minus expectation x times y minus expectation y. Okay, so what does that mean? Okay, here's an example. Let's suppose there are joint random variable x and y defined like this. This is the random variable. This is another example, and this is another example. Like this is the point. Okay, in the first case, if the greater values of one variable mainly corresponds with the greater values of the other variable like this, the same hold for the lesser case like this. The covariance matrix will be the positive values, and in this case it provides the high covariance. In the opposite case, when the greater values of one variable mainly corresponds to the less values to the other variable like this, in this case the variable tended to show the opposite behavior between them. So in this case, covariance is negative like this. What about this? If the two variables are independent, it means that these values and these values don't have any relationship. The covariance becomes 0. So that's why we learn the covariance of the random variable, because if we know the covariance, we can understand the shape of the data, training data, distribution, something like that. Okay, so this is a covariance matrix. Okay, so Here's some common probability distribution. There are very popular probability distribution. First one is a Bernoulli probability distribution. The second one is a Gaussian. The Bernoulli distribution models the probability of the success for the single event, like the binary event. For example, it's a coin flip. We can see the example in the next slide. And the Gaussian distribution or normal distribution models a very wide variety of phenomena, the distribution of population, sampling distribution, something like that. So this is the two very well-known probability distribution. Okay, let's see the Bernoulli distribution first. The probability mass function of the Bernoulli distribution is represented as follows. In this case, in this case, expectation becomes the probability itself, like this. The variance becomes the probability times 1 minus probability, like this. Okay, so let's say theta is the probability. Okay, let's see the example. Let's suppose the bias coin in which the probability of the head is equal to the 0.8, like that. In this case, the probability of the tails is going to be the 0.2 because the following this equation, and the expectation of the random variable x will be the 0.5, 0.8, and variance of expectation will be the 0.16, like this. So this is the Bernoulli distribution, something like that. So this is the visualization of the Bernoulli distribution. In this case, there are two discrete random variables. The first one is head case, second one is tail case, like that. So in this case, this probability was the 0.8, this probability was the 0.2, right? So this is the visualization of the Bernoulli distribution. It is easily represented by like this. It means that this Bernoulli distribution can be determined with only single variable p. P is equal to theta in this case. Okay, so this is the Bernoulli distribution. Another popular distribution is the Gaussian distribution or normal distribution. The definition of Gaussian distribution is as follows. So which is parameterize the mean value sigma, which determine the location of distribution, and the variance sigma, which control the how wide or narrow the distribution is. So in this definition, the mu is here, the square of sigma is here. Okay, so this is the definition of the Gaussian distribution. So the expectation of the Gaussian random variable can be represented mu. The variance of the random variable x can be represented the square sigma, like this. Okay, let's see the visualization of a Gaussian distribution. As you can see here, as varying the mu and sigma values like this, the shape of Gaussian distribution is varying. For example, like this. When mu is 0 and sigma square was 1, the shape of Gaussian distribution is like this. As you can see here, these two Gaussian distributions have the same mean values but has the different shape, like this. If we choose the different mu values like this, the distribution will move to the other position like this. So this is the another shape of the Gaussian distribution. Okay, so why is the Gaussian distribution is important? If we assume that the random variable is derived from the Gaussian distribution, we can make so many equations or problems more tractable. Furthermore, in many cases, the Gaussian distribution well approximated the real distribution of the data, so that's why we run the Gaussian distribution in machine learning and deep learning stuff. The Gaussian distribution is also related to the central limit theorem, which means that the sum of many random independent variable converges in the distribution of Gaussian. Okay, so it means that if we assume that the some training data set follows the Gaussian distribution, it will make sense if there are so many independent variables. Okay, so that's why we learned the Gaussian distribution. So there are several different forms of the proof used for the central limit theorem. So it is the basic of the sampling theorem. So please study what is central limit theorem before starting our next chapter. Like that. Okay, this is the end of the basic linear algebra and probability theorem. In fact, we cannot deal with the whole of the linear algebra and probability theory within 1 hour. Nevertheless, so when we learn propose the machine learning algorithm, the linear algebra and the probability theory are kinds of the weapon you can use. So I would suggest study the linear algebra and probability theory as much as you can. It will be a good starting point of machine learning, pattern recognition, or deep learning. Thank you very much. In the next lecture, we will talk about the supervised learning, such as regression, linear regression, classification, and the fundamental concepts of the machine learning. Thank you.